So let's talk about molecular shapes and polarity. We've talked a little bit about polar bonds. If we have two atoms that have different electronegativities, they're going to share the electrons in that covalent bond unequally. Here we've got chlorine and hydrogen. Chlorine is more electronegative. It draws the electrons towards itself. And so if we look at the electron density around these atoms in the molecule, we see there's more electron density at this end. And that results in this end of the molecule having a slight negative charge and this having a slight positive charge. So that's not so hard. That's just two-dimensional. When we get into polyatomic molecules, then the polarity of the molecule is going to depend on the geometry. So if we have individual polar bonds, but they are going in opposite directions and cancel each other out, then the molecule will be nonpolar. So the one that's easiest to understand is carbon dioxide. So here we've got carbon dioxide, and each of these bonds is polar with oxygen being more negative. But overall, when we look at the electron density, we see that carbon dioxide is symmetrical. We don't have one end that's different than the other. And the reason for this is that this polar bond is pulling the electrons this way, and this polar bond is pulling them the other way. But the dipole moment, which is how we measure how strong that pull is, the dipole moments are the same and in opposite directions, and so they cancel each other out. So one way I like to think about that is like playing tug of war. So if you had a person over here and a person over here, and they're playing tug of war, and this is the flag that has to cross a line to choose the winner. If these two guys are equally strong, the flag's not going to move, and it's just going to be a standstill. If one of these guys is stronger than the other, then the whole thing will move and we'll have a polar molecule. If the molecule's not symmetrical, like in in water, here, because of those lone pairs that aren't shown here, this is a bent structure, and so now these polar bonds are not pulling in exactly the opposite direction, and so they don't cancel out. So if you're familiar with vector addition in math, that's exactly what's happening here. Dipole moments have a magnitude and a direction, and both of them matter when we're adding them together. So the more rigorous way of determining molecular polarity is first you draw the Lewis structure, you see if the bonds are polar, well you find its molecular geometry, you find that the bonds are polar, and then you determine if those polar bonds add up to form a net dipole moment or not. If they sum to zero, the molecule's nonpolar. If they don't, it's polar. So that's more rigorous, but also requires a lot of thinking. So I'm going to go ahead and jump through to this part. So if you want to look at vector addition, you can watch the other video. This is what works, actually works all the way through OChem. And if you get to PChem, they'll teach you other stuff anyway. So here's my shortcut to molecular polarity. It doesn't work all the time, but it works probably like 95, 97%, something like that, which is good enough. So a molecule is nonpolar if both of these things are true. There's no lone pairs on the central atom, and all the atoms bonded to the central atom.
There's only like 5 people connected in class.
If all of the atoms bonded to the central atom are either the same or they have the same electronegativity. Most of the time, it's just going to be, are they the same or not? Let's see. So let's do an example here and determine if CF4 is polar. We still have to draw the Lewis structure. So the Lewis structure for this is going to be carbon in the middle, and we've got 4 fluorines, and those are going to be around the outside. And then if we count up the valence electrons and put all the lone pairs in, I'm not going to do this in detail because we've covered that already. So there's our Lewis structure. So then we ask ourselves those two questions. Are there any lone pairs on the central atom? No, they're not. Are these atoms that are bonded to the central atom all the same? Yes, they are. So there's no lone pairs and the atoms are the same, therefore this is nonpolar. So the reason that works is when all of these are the same element or the same electronegativity, that means the magnitude of all these vectors is the same. If there are no lone pairs, that means that they're distributed evenly in three-dimensional space, and so they will add up to 0. If we look at, if we change this up a little bit, and maybe put a hydrogen in there, so that's for that one. So the first condition of no lone pairs on the central atom is still true, but now all of these atoms are not the same. Fluorine is very electronegative and is going to have a large magnitude, pulling electrons away from carbon. Carbon and hydrogen are actually close enough in electronegativity that that bond is considered nonpolar. And that's one that you should remember. Carbon and hydrogen, nonpolar bond. There are other combinations of nonmetals that give nonpolar bonds, but they really don't show up that often. Carbon and hydrogen shows up so much that it's definitely worth remembering. So this then is a polar molecule because even though the vectors are distributed evenly in three-dimensional space, one of them is weaker than the others, and so they don't add up to 0. If we have something like ammonia, for ammonia, didn't mean to do that. For ammonia, the first condition is not true. There's a lone pair. So actually we can just stop and say this is polar. With very few exceptions, if there's a lone pair on the central atom, the molecule's polar. The second condition is true, that all of these atoms are the same, but that doesn't matter because this lone pair makes the molecule lopsided, and so the vectors, not having a vector on this side, those guys will not add up to 0, and we'll have a polar molecule. Anybody have any questions about that? Because identifying polar and nonpolar molecules is pretty important.
I have a question.
Okay.
Actually. So it says if it's two of the same, that it would be nonpolar, but is that true even if the molecule is bent? Because I thought if it was bent, it was supposed to be polar.
Yeah, so with water, which is the classic example of that, water is, when we look at the Lewis structure, we may or may not recognize that its shape is bent, but we see that there's 2 lone pairs on the central atom, and it's those 2 lone pairs that cause it to be bent and cause it to be lopsided. And so even though the 2 hydrogens are the same, the vectors are not distributed evenly in 3-dimensional space, and so they add up to a net dipole. And so this one's polar. Does that answer your question?
Yeah, I was just confused because in one of the homework questions it was asking if SBR2 was polar or non-polar, and I thought it would be the same.
Mm-hmm.
I put what the book was saying, non-polar.
Yeah, so the key to this method is you have to look at the Lewis structure because the lone pairs on the central atom are super, super important. Yeah. So drawing Lewis structures is really important. Anybody else have any questions about this?
What is the second
Condition?
the first one is lone pair. The second one, if you can go back to that screen when you had written it.
There it is. So all the atoms bonded to the central atom are the same.
Right.
And this is kind of the fine print, or have the same electronegativity. That doesn't come up very often, but.
Okay.
And again, there are exceptions to this. One that I can think of just off the top of my head is something like xenon tetrafluoride. Which actually has 2 lone pairs on the xenon. And so this is one where my shortcut would give you the wrong answer. But this is a really strange molecule, doesn't show up very much. This is actually nonpolar, because of its geometry. So those 2 lone pairs are on opposite sides of the xenon atom, and so we get a square planar geometry. And so even with the lone pairs, the vectors are distributed equally in 3-dimensional space. They do make a square. And so if you look at this flat square and you imagine, let's do a different color here. You imagine this guy pulling this way and pulling this way and pulling this way and pulling that way. 4 equally strong guys pulling. Nobody's going to win. The xenon's just going to stay in the middle, right? Vector addition is a lot easier to understand in 2 dimensions than in 3 dimensions. Any other questions? So polarity is really important because it drastically affects the properties of molecules. Polar and nonpolar molecules generally will not mix together. And this is what happens with oil and water. And, go in the kitchen and try this after lecture if you want to, or if you've got Italian salad dressing that doesn't have an emulsifier in it. The oil always rises to the top and the water sits on the bottom. And you can shake this up as long as you want, but as soon as you stop shaking it, it will begin to separate out again. And that's because the water molecules are polar. And so they attract each other just like magnets. We're familiar with magnets. The south pole of one magnet is attracted to the north pole of the other magnet, and they'll stick together. Depending on the strength of the magnet, they'll stick together very strongly. And so these polar molecules act like magnets, except it's electrical charge. So we've got a partial positive charge here and a partial negative charge here. In a way, it's similar to what happens with ions, except this is only a partial charge. So even in a very strong molecule, that might be, 1/10 of a positive charge and 1/10 of a negative charge. It's small. It's not like a +1, -1. And so this attraction is much weaker than an ionic bond, and yet it's significant. Nonpolar molecules don't have those charges on them, and we'll talk about how they get attracted to each other in chapter 12, but they're not attracted in this way. And so we can think of this as being a lot like what would happen if you'd mix regular glass marbles with magnetic marbles. And even if you've never done this, you can probably imagine the magnetic marbles are going to stick together, and they're going to squeeze out the glass marbles because the glass marbles just aren't attracted to each other. That's what's happening with the water and the oil. The water molecules are very attracted to each other like the magnetic marbles, and so they push the oil out. The oil rises to the top because it's less dense. There are other nonpolar substances that are more dense and will go to the bottom. but they will still separate into layers. Any questions? So you probably know from experience that grease and oil don't rinse off with water. If you've got butter on your fingers or Crisco, if you've been making a cake or something, and you go and try to rinse it off with water, it just stays on your hand, right? You got to use soap. And so I always think it's interesting to talk about how does soap work. So the water is nonpolar, the grease on your hands is polar, and so they're not going to mix together. Soap molecules are sort of like double agents. They have a polar end and then this long nonpolar tail. And so what happens is these long nonpolar tails can get into the grease, and the polar heads will be on the outside. And there's a better picture of this in a later chapter, but what happens is you've got a whole bunch of these soap molecules. This is a two-dimensional representation. Maybe this is the grease. It looks like butter, doesn't it? So the nonpolar tail of the soap will mix in with the butter. And then the nonpolar heads stick out on the outside. Well, this will make a little globule or micelle, and because it's got polar heads on the outside, that interacts with the water very nicely, and so the soap molecules are essentially sneaking small pieces of butter into the water, and that allows them to be washed away. Any questions?